Okay, welcome back to Malware Analysis. I am Jay Lavanya, Assistant Professor of CSC Department. So today in this video, we are going to discuss the Unit 5. The topic is Anti-Malware Analysis. In that, we are going to discuss on the topics like anti-debugging, anti-VM, anti-emulation, and anti-dumping. So these are the four major topics under this anti-malware analysis we are going to discuss. So let's dive into the topic. The First of all, what is meant by anti-debugging, right? So in malware, it refers to a set of techniques used by the malicious software to detect and prevent some security researchers and analysts from using debuggers to reverse the engineer, understand and analyze its behavior. Okay, and this malware authors employ anti-debugging to make the malware harder to analyze, detect, and block by altering its behavior or crashing the debugger or slowing down the analysis process. So the common techniques include like using some system API, like is debugger present or not, that function by means of that we can able to use it. And second, by analyzing the timing and performance, right? Or checking for some debugger specific artifact or such things. And how this anti-debugging works. So here we also use some specific anti-VM that is a technique, right, that is used in malware and other software to detect if it is running on a virtual machine, that is VM, rather than a physical machine, and if so, to alter its behavior or to terminate the execution. So this is done to thwart malware analysis in virtual environments. So which are common for some security researchers. Techniques involve checking for VM-specific artifacts like a unique user activity or the registry entries, and even manipulating CPU timing to identify a virtualized environment. Okay, so this is the common, or general intro of this anti-debugging. And the next slide discusses on what are the purposes of anti-VM techniques. So there are three such cases. First of all, is that thwarting analysis. Second one, evading detection. Third one, targeted attacks, right? So first of all, what is meant by thwarting analysis? So malware authors use anti-VM to prevent the security analyst from easily studying their malicious code in isolated virtual environments like sandboxes or virtual machines. And second, like evading detection by identifying as running on a physical machine, malware can potentially avoid the detection by the behavior analysis tools that might flag activity within a VM as suspicious, right? And third one, targeted attacks. So in some cases, malware may have some different functions or payloads depending on whether it's running on a physical system or a virtualized one, right? So these are the main purposes of anti-VM techniques: thwarting analysis, evading detection, and third one, targeted attacks, right? Okay, next slide. Next slide, how the malware can use various methods to detect a virtualized environment. That is how the anti-VM techniques work. First of all, through artifacts, and the second, like timing and performance, and third, like user activity, and fourth one, like hardware check, and last one, that is instruction sets, right? So first of all, artifacts. So searching for some files or drivers or registry entries common to specific VM software like VMware or virtual box. Okay. And second, like timing and performance. So this involves exploiting differences in CPU cycle counts or execution timing between the physical and virtual missions. And third, that is user activity. So here checking for some specific default username, few files, or a lack of USB device history, all that is common in newly set up analysis environments. And next, like hardware checks. So inspecting the hardware attributes such as the computer model to see if they indicate a cloud or a virtualized host. And next, like instruction set using some specific CPU instructions such as SLDT and SD, which may behave differently or reveal the presence of a VM. Okay, like examples, commonly used here is that like tools and libraries, like anti-VM at GitHub, right? At GitHub, I think most probably you have used that project that includes an IDE Pro plugin to identify anti-VM behavior. And next, like PyDefender, a Python-based tool that detects the VM and sandbox environments using some various checks such as VM-specific user checks and recent file activity. And next, like VM Aware, an advanced VM detection library and command line tool designed to provide details about the running environment. Dot what he also used to say. And next, like VM ABAP, an advanced VM detection library and command line tool that is designed to provide details about the running environment. Okay, so these are the things how this anti-malware works. Okay, yeah. And next is that uses anti-debugging, like why we are going for these kind of ads. But before that, a malware uses various methods to detect if it is running under a debugger, including API-based checks, like calling Windows API function like is debugger present, as I've given during the intro class, I mean introduction of this particular video, is debugger present or check the remote debugger present, which returns a value indicating whether a debugger is attached. And second, the process environment block or TEB inspection we used to say. So here, examine TEB, that is a data structure, contain information about a process for debugger flags or other indicators. Okay, and next, like timing these checks. So here, if you take like measuring the execution time of the code segment or the debuggers, often introduce some delays. So if the execution time is significantly longer than the expected, the malware can infer is being a debug. Okay. And next, like interpret or exception handling. So maliciously causing and catching the exceptions to disrupt the debugger or leveraging structured exception handling to slow down the process. And next, like custom checks, creating custom checks, such as looking for known debugger process or image names in memory. Okay, so here, why we are using the anti-malware analysis is that first one, preventing analysis. primary goal is to prevent security researchers from understanding the malware's functionality, mechanisms, and capabilities. And second, evade detection and removal. Here, by making analysis difficult, malware authors make it harder for the security teams to develop effective detection and removal methods. And next, like protecting a malicious behavior. So malware can alter its behavior, such as performing harmless actions or closing itself if it detects a debugger. Okay, and what are the consequences for analysts, right? If they are using this anti-debugging, slower analysis because anti-debugging techniques primarily aim to slow down the reverse engineering process that makes it more time consuming. And next, like increased effort, detecting and bypassing some anti-debugging code patterns can be a manual, error-prone, and expensive process, as noted in some research in automatic deduction techniques, right? And next, yeah, and if you take some common anti-debugging techniques that is applicable to some real-time applications, first of all, a debugger deduction flags. So checking for some specific flags or internal data structures within the operating system that indicate a debugger is attached to the process. For example, on Windows is debugger present function or checking the PEB can be used, like process environment block can be used, and timing based checks. So debugger often introduce delays in execution, which can be detected by measuring the time taken for certain operations. So if execution time exceeds a predefined threshold, it might indicate the presence of a debugger. Okay. Third, like self-modifying code, modifying the application's code at runtime in a way that would be disrupted or detected by a debugger. So this can involve encrypting and decrypting the code sections or dynamically generating code. And next, like checksums and integrity checks, verifying the integrity of critical code sections or data structures using some checksums. If a debugger modifies these sections, the checksum will no longer match, triggering a defensive reaction. And next application like API hooking uh, deduction. So debuggers often rely on hooking systems. So APIs to monitor or manipulate the application's behavior. Detecting these hooks can indicate the presence of a debugger. And next, like anti-attach mechanisms, implementing measures to prevent the debuggers from attaching to the application's process in the first place. So this can involve using some specific system calls or the techniques to make the process unattachable. Okay, and next, like exception handling, exploitation, deliberately triggering exceptions or unexpected behavior that debuggers might handle differently than the normal execution, like allowing for some detection. Okay, and next, like virtual machine detection, if the real-time application is designed to run in a specific environment, checking for some indicators of a virtual machine. Say the example like specific hardware identifier or the network interface card that can be used as a proxy for potential debugging attacks. And next, like obfuscation and encryption. While not strictly anti-debugging, obfuscating and encrypting critical code and data that makes it significantly harder for attackers to understand and manipulate the even if they manage to attach a debugger. Okay, and next, like reactive measures upon the detection. So when a debugger is detected, the application can take various reactive measures. First one, like termination. So gracefully terminating the application to prevent further analysis. And next, altered behavior, like changing the application's behavior to mislead or like confuse the attacker, such as displaying incorrect data or entering into a safe mode. Okay, and next, like data wiping, securely wiping sensitive data stored on the device to prevent its exfiltration. Yeah, and next, like report. If you take reporting, reporting the detection of a debugger to a backend server for further analysis or fraud detection. So the effectiveness of anti-debugging techniques is enhanced by combining multiple methods, distributing them throughout the application, and implementing them at different API layers. Example, Java, native, and assembly. Okay, so it is important to know that while anti-debugging techniques can significantly increase the difficulty of reverse engineering, they do not offer absolute protection and can be circumvented by determining the attacks. Okay, so this is all about the anti debugging. Yeah, okay. So next slide. Now let us discuss on anti-VM. So anti-VM, it is a technique that is used in malware and other software to detect if it is running on a virtual machine rather than a physical machine, and if so, to alter its behavior or to terminate the execution. And this is done to thwart malware analysis in virtual environments, which are common for some security researchers, right? And uh, like techniques involve checking for some VM specific artifacts, unique user activity, registry entries, and even manipulating CPU timing to identify a virtualized environment. Okay, the next slide. We will discuss on what are the purpose of anti-VM techniques. So first of all, it's thwarting analysis, second, evading detection, and third, like targeted attacks. Okay. So what does mean by thwarting analysis? Malware authors use some anti-VM to prevent some security analysts from easily studying these malicious code in isolated virtual environments like sandboxes or virtual machine. That is VM. Okay. And next, second, like evading detection by identifying as running on a physical machine. Malware can potentially avoid the detection by behavior analysis tools that might flag the activity within a VM as suspicious, right? And third one, like targeted attacks. In some cases, malware may have different functions or payloads depending on whether it's running on a physical system or a virtualized one, right? So these are the purposes of anti-VM techniques. Okay, in next slide, we will discuss on how this anti-VM works, like based on artifacts or the timing and performance, and third, like based on user activity, fourth, like hardware checks, and last one, like instruction set. Okay, So malware uses these methods. So first, like artifact, searching for files, drivers, or registry entries that is common to you know some VM software like VMware or the virtual box. And second, like timing and performance. Right? So timing and performance, exploiting differences in CPU cycle count or execution timing between the physical and virtual machines. And third, like user activity, checking for some specific default username, few files or a lack of USB device history. All common is a newly set up analysis environments. And next, like hardware checks, inspecting the hardware attributes such as the computer model to see if they indicate a cloud or a virtualized host. And next one, like instruction sets, using some specific CPU instructions such as SLDT and ST, which may behave differently or reveal the presence of a VM. Okay, what are the common examples of this tools or the libraries used in anti-VM? So first thing, like GitHub project that includes an IDA Pro plugin to identify the anti-VM behavior. Okay, and next one like PyDefender, a Python-based tool that detects the VM and sandbox environments using some various checks. Okay, such as VM specific user checks and a recent file activity. Okay, and next one like VM Aware, an advanced VM detection library and command line tool designed to provide details about the running environment. Okay, so this is how the anti VM works. Okay, next is that anti emulation. Okay, so anti-emulation refers to a set of techniques used to detect and evade the analysis within an emulated environment. So these methods are used by both the malware authors and legitimate software developers for the different purposes. uh, why it is used by the malware if you take. So malware frequently uses anti-emulation to avoid the detection by some security tools, which often uses of emulators and sandboxes to analyze the suspicious files in a safe environment. By detecting if it is running in an emulator, malware can stop its malicious activity that remain dormant and avoid being flagged as malicious. And next, like used by legitimate software vendors, software companies use this anti-emulation for intellectual property protection, preventing the reverse engineering and stopping the piracy. For mobile applications, it can be a vital technique for safeguarding some sensitive data. Okay, so this is about the anti-emulation, right? So in this slide, we will see about what are the common anti-emulation techniques like unique identifier, build information, system properties, and file system artifact. Okay, so first of all, the programs what it will do is that you know like checking for system properties for artifacts that indicate an emulator environment. Okay, so unique identifier in this case checking the device ID, phone number, or IMEI can reveal an emulator, as these identifiers are often generic or have a predictable pattern. Okay, And next, like build information. Malicious apps often check build properties like build.model or build.fingerprint for strings such as emulator, Google underscore SDK, or Jenny Motion, right? And next, like system properties. Programs look for some unusual property values such as a hardware model named goldfish or bootloader listed as unknown, which are common in emulators, right? And next, like file system artifacts. The presence of files or directories known to exist only in some specific emulators can serve as a red flag. Okay. And next, like if you're going for detecting timing and performance anomalies, emulators often handle a code execution that is slower than the physical hardware. Okay, like which can be detected by monitoring this time it takes to complete a task. Like instruction time discrepancies, some techniques measure the precise timing of specific CPU instructions in an emulated environment. These instructions may take a different amount of time to execute due to the overhead of binary translation. And next, like time lock puzzles. And this technique involves a computational intensive puzzle that takes a specific amount of time to solve. An antivirus emulator may skip or solve it too quickly, revealing that the code is not running on a physical device. And next, like exploiting unimplemented or fake features. Like many emulators are incomplete and do not fully replicate the behavior of a real system. Okay, like Appstore API calls malware may invoke a seldom used system API call and check for an unexpected error code or a generic return value, which indicates that the emulator's designers did not fully implement that function. And next, invalid instructions. Attempting to execute a privileged CPU instruction in a user mode application can reveal the emulation. On real hardware, this could fail with an exception, but some emulators may handle it differently, right? And environment specific needs, programs can look for signs that a dynamic analysis tool is running alongside them. First of all, like debugger detection. So checking if the debugger is connected to the process. For example, the Android debugger bridge, that is ADB, is frequently used by the security researchers. And next, like installer checks. An app can check if it was installed from an official app store, if it was installed by an ADP or another site loading method. It might be running in an analysis environment. Okay. And now, okay, like real-time applications of anti-emulation techniques. First one, software protection. So legitimate software can use some anti-emulation to prevent the reverse engineering and to protect the intellectual property by making it harder to analyze or copy. And next, like malware analysis. Security tools use this emulation to sandbox and analyze potentially harmful software. And next, like anti-emulation techniques that can be employed by the malware itself to detect that it is in a sandbox and alter its behavior, or by security tools to more accurately detect and analyze the malware's actions. And And next, like digital forensics anti-emulation can be used in digital investigations to ensure that the software's actions are not being manipulated in an emulated environment, providing more accurate results in a real world scenario. Okay, so these are the common applications. And next topic is that we will discuss on anti-dumping. Yeah, okay. So what is anti-dumping? So malware uses anti-dumping techniques to prevent easy memory dumping or to detect when a debugger or the memory dumper tries to extract the decrypted payload. This protects the malware's inner workings and hides the payloads or the keys. Okay, yeah. And next, let us discuss on what are the common anti-dumping techniques in malware. So first, integrity checks or hashing. So malware calculates the hashes, example CRC or MD5 of its own code section. If the hash differs due to tampering or dumping, it alters the behavior or the crashes. And second, like API smoking or the deduction, it detects the common debugging or dumping tools via API calls like is debugger present or check the remote debugger present, and detects the suspicious memory access or debugger artifacts, right? And third one, like memory access restrictions, using some virtual protect with page no access or page guard to trap the access attempts. And next, like self-modifying code or dynamic change memory permissions to confuse the dumpers. And next, timing shifts. It uses some get ticket, count or query performance counter to detect the slowdowns caused by the debugger or the dumping, right? And next, like code encryption with the dynamic keys. Keys or routine change each execution to prevent the static dumps from the working. And apart from that, we have the self-debugging. The malware creates a debugger thread for itself to prevent other. Yeah, okay. So this is some of code encryption with dynamic keys. Okay. And next, one more thing, that is self-debugging. The malware creates a debugger thread for itself to prevent other debuggers. And next, like thread hijacking or multiple threads. It uses multiple threads or hijacks other threads to complicate dumping. Okay, yeah. And next, like how to bypass anti-debug dumping in x86 DBG, right? So first one, patch, yeah, patch integrity check. Okay, so find the integrity check routine and patch the code to bypass or always return some integrity. Okay, and second, like hide debugger presence. Use some plugin or patch API called like is debug present to return the false. And it uses x86 which is built-in anti-debugging plugins. And third, like dump memory at runtime. So wait until the malware fully decrypts or unpacks the payloads. So dump the memory only after the anti-dump checks are over. And the next one, like use the hardware breakpoints instead of a software breakpoints. Hardware breakpoints are less detectable rather than the software breakpoint. And next, like usual manual mapping or stealth debugging. Okay, so debug in a way that avoids modifying the memory pages or triggers no access violations. And next, that one more thing like patch page guard or no access protection. Detect and remove the guard or change the page protection manually. Example like patching is debugger present in x86 is search for the codes is debugger present in the assembly. When found, patch the code to always return 0, move EAX 0, return false, now debug. So you can use the by editing the instruction, right? Okay. Now let us see what the real-time applications in practice to bypass this, use the anti-dumping process. First, like automated monitoring and data analytics. System uses big data and machine learning to constantly monitor or import the prices and the trade flow, identifying the potential dumping activities much faster than the manual check. And next, like early warning system, these systems flag the products with some suspicious price pattern that deviate significantly from their normal domestic or third country prices. And next, like accelerated investigation tools, digital platforms and data analytics are used to quickly process some large data sets of input information and economic data, speeding up the investigation period. And the next one, like provisional measures. If immediate threat of injury exists, government can impose provisional measures to prevent further damage, which while the full investigations is underway, right? And next application, like trade remedy data portals. The World Trade Organization, that is WTO, maintains the data portals like their trade remedies data portal, which provide the real-time information on active anti-dumping measures and investigations globally. And next, like digital platforms for fillings, companies and investigators use online portal to submit the documentation and data during the investigation process. Okay, like example scenario, if you take like a domestic manufacturer in India identifies a sudden surge of chemical product from China at a significant lower price than the normal value. For this, like flagging the issue or the rapid assessment or the faster investigation or through some provisional duty, we can able to anti-dump it, right? Okay, so these are the things of applications of anti-dumping. Okay, yeah. So in this, uh, I mean, video, we have discussed about the various anti-malware techniques that is used, right? So the first of all, like we have discussed on uh, what is mean by like anti-debugging, and it's like anti-VM, or what is the purpose of anti-VM techniques, and how does this anti-VM works, right? And next we have discussed on some uh, the purpose of anti-VM techniques and how does it work and what are the examples of tools and libraries that is used and what are the real-time scenarios of it and how it is used in the real time. And next topic we have discussed on anti-emulation and what is the definition and how it is used by the malware, right? And what is used by legitimate software vendors and common anti-emulation techniques. Like example, we have unique identifier, built information system properties, and last, like detecting the timing and performance anomalies, okay, and environment specific checks. And last topic we have discussed is that anti-dumping. So here, what are the common anti-dumping techniques in malware, right? And then we have discussed how to bypass this anti-dumping in x86 PG, right? And apart from the, what are the example like patching, is debugger is present or not? Okay, and what are the real-time cases in occurred in the in the example scenario we have discussed, right? I hope this video will be very useful. In deep time, we will see the remaining topics in the upcoming session. So thank you all. I hope you have enjoyed this video. Thank you so much.